Hello, today we're going to review for the AP Chemistry exam by going through the free response from the 2019 chemistry test. Let's start with the first of 3 long free responses. Each one of them is worth 10 points total. So we have urea, and it's widely used in chemical fertilizers, and they give us the Lewis electron dot diagram. And then it wants us to identify the hybridization of the valence orbitals of the carbon atom. So that's this one. So that carbon atom has 3 areas of bonding around it, 1, 2, 3. So that's S and 2 P's, or we write it sp2. So when it asks for hybridization, it's looking for the letters and numbers if there are any. The other thing they could ask there is the geometry instead, and the geometry would be trigonal planar. sp2 is always trigonal planar. Even though it looks like it's a T-shaped, it's not. They like to draw it so everything's right angles, even though very few things are actually right angles. And then for part B, urea has a really high solubility in water due to its ability to form hydrogen bonds, and then they give you a drawing with a urea molecule and 4 water molecules. It says to draw 1 dashed line to indicate a possible location for hydrogen bonding. So there were a couple different places you could do this actually, because remember hydrogen bonding is Fon. So these hydrogens on the urea molecule can hydrogen bond with a source of electrons on a different molecule. So you could have it like to that oxygen or to that oxygen. This one I think is a little hard to show, but if you were to somehow show that it's hydrogen bonding with the oxygen, then you're good. I would just be careful with that one in particular, because you don't want to mistake that you're putting it towards another hydrogen. That's not correct. You could have also, because the lone pairs on the oxygen and urea, you could have also drawn a dotted line from a hydrogen on water to that oxygen. So either of these would have been good. So there were a lot of options, but you just had to pick one of them for this question. Okay, so now we're dissolving urea. So a solid to aqueous, dissolving. The student determines, so we've got a mass of urea can dissolve in water to make 5 milliliters of a saturated solution. Calculate the concentration. Okay, so basically anytime you see grams, you should change it to moles. It's very rare that you don't. And they give you the molar mass. Look how nice of them. Grams per mole. So then when you divide, you get the moles to 3 sig figs is 0.0897. But we don't want moles, we want moles per liter, the concentration. So you would divide by the liters. So 5 milliliters is 0.005 liters to give us molarity, 17.9. Really high molarity, actually. That's because it's very soluble. It can dissolve a lot. So this one was actually 2 points on the 2019 test, which was nice. Usually if you have to do more than one step, like more than one significant step, then it will be more than 1 point, but not always. And then the student determines that the concentration in a saturated solution at 25 degrees Celsius, so we're changing temperatures now. So at a higher temperature, it's now 19.8. Is the dissolution endothermic or exothermic, and justify in terms of Le Chatelier's principle. So we're saying at higher temperatures, it dissolves more. So when you increase the temperature, you're getting more on the product side. It's dissolving more. Higher temperature, it will move away from the heat. So if we're going to the product side, then the heat must be on the reactant side if we're going away from it when the temperature increases. So you would say, if I were to phrase this question, you would say the dissolution of urea is endothermic because as you increase the temperature, the reaction moves away from the heat and towards the product side, according to Le Chatelier's principle. Le Chatelier and Coulomb are your two guys. So those are the ones you definitely want to reuse their names when you can. Okay, so they give us this equipment, and we know that the specific heat of the solution is 4.18 joules per gram Celsius. List the measurements that are required to be made during the experiment. We're trying to find the heat of solution. This is like a hand warmer design lab. So you would need to do Q equals MC delta T. And we're trying to find the heat. And they gave us C. So all we need to do, the measurements, we need to measure the mass of the urea, and you would need to measure the change in temperature. So I think the most accurate way to answer this is to say record the temperature before and then the temperature after, because those are the specific measurements. Then you can subtract to find your change, but that's a calculation, that's not a measurement. Let me rewrite the equation really quick. It's H2NCON2H, I'm sorry, NH2. Solid goes to aqueous, okay. So then they give us the entropy change for this process is 70.1 joules per mole Kelvin. Calculate the absolute molar entropy of urea. This equation is on the formula sheet, and it is the products minus reactants. So you would do products is their aqueous, that's the thing we don't know, minus our reactants, which is a solid, is equal to our overall. So we get, when we solve for this question mark, 174.7. Oh, I could have done that in my head. Anyway, so you just add the 104.6 to each side. Okay, so then it says, using particle level reasoning, explain why the delta S of the solution is positive for the dissolution of urea in water. Positive. So that 70.1 is positive. It's because those particles are splitting apart and becoming more disorganized, more spread out in the solution. That gives it more entropy. So anytime you have more moles of gas or more moles of liquid compared to a solid, aqueous things tend to be more disorganized than solid things. Now, part H, the student claims that delta S contributes to the thermodynamic favorability. Blech. Remember, whenever you see that, you immediately want to think delta G is negative. For the dissolution of urea, use the thermodynamic information above to support the student's claim. Okay, well, so if we want delta G to be negative, right, it's equal to the delta H minus T delta S. Well, we know the temperature is positive. It has to be positive because it's in Kelvin. And delta S, they told us, was positive. Well, that's a good thing because we have to subtract this whole term, right? So having delta S be positive helps delta G be negative. So yes, the fact that delta S is positive contributes to delta G being negative because that term is subtracted from the delta H. I would suggest for these questions actually writing out the equation because it makes it a little easier for you to explain. Now let's look at our second long Fourier response. Okay, so question 2 is all about the halogens. So we have bromine, chlorine, fluorine, and iodine. Circular formula of the molecule that has the longest bond length. So anytime you have a series of elements in the same group, your answer, your justification, has something to do with the number of energy levels. Because the valence shell is further away from the nucleus, the more energy levels there are. So when you have something with I2, has the most energy levels of that set, it's going to have the longest bond length because it's further away. When you have two iodine atoms, they are further away from each other because there's more energy levels that are in between their nuclei. Versus fluorine, which are much smaller atoms, they can get physically much closer together than the iodine atoms can. Okay, so now the teacher wants to prepare BR2, 3 reagents, and they give us 3 half reactions. Write the balanced equation for the thermodynamically favorable reaction. So delta G is negative. Whenever you see thermodynamically favorable, delta G is negative. That will produce BR2. Okay, so we already know that this reaction, the first one, has to be used. It's the only one with bromine, and we need to flip it. So you're going to have 2 bromides forming that BR2 that we're trying to form, and 2 electrons. But since we flipped it to oxidation, it's now a negative 1.07. So we're producing BR2 when the teacher combines 2 of the reagents. Justify that the reaction is thermodynamically favorable by calculating the value of E. So if delta G is negative, we need the cell potential to be positive. Okay, and that's because of this equation here, delta G equals negative NFE. So that negative sign indicates that whenever delta G is negative, cell potential is positive. So in order to make the overall potential positive, I need to add it to this chlorine reaction. The Cl2 plus 2 electrons yields the 2 chloride ions because it's a positive 1.36, and when you add those together, you get sorry, I wrote that bit wrong. We get, it's 1.36, there we go. So when you do add those 2 together, you get a positive 0.29 volts overall. And when you add up the 2 reactions, the electrons cancel out, and you are left with our overall reaction, that is the 2 bromides plus the chlorine gas yields the bromide and or the bromine and the 2 chlorides. So there's our overall, and there's our cell potential. And you should indicate that, so because it's positive value, that means that it is thermodynamically favorable. You could also mention, because it's a positive cell potential, it's a voltaic cell, which happens spontaneously, that works as well. But you need to make sure that you do both of those things there. Okay, the boiling point of bromine is 332, whereas the boiling point of BrCl is 278. Explain the difference in terms of intermolecular forces present. This is a good example of something where, like, if you were stumped by B, keep going. Don't give up on the question. Just keep reading through the parts, because there can be completely different things as you're going through. So now we're switching gears to intermolecular forces. Bromine is completely symmetrical and nonpolar, so it only has those London dispersion forces, whereas BrCl is slightly polar, and it has London dispersion forces and dipole-dipole interactions. So that's a point right there. It's just stating what intermolecular forces they have. Then we have to explain the difference. Right? So this one actually has a higher boiling point, even though the BRCL has dipole-dipole interactions. And that's because whenever you're looking at London dispersion, it always has to do with polarizability. So because the two bromine atoms have a lot more electrons put together than the bromine and a chlorine, and we're looking at total electrons, not just valence electrons. So the bromine has a lot more total electrons, so it's more polarizable, and therefore can form stronger London dispersion forces. Okay, so this BRCL can decompose into bromine and chlorine, and I see a value. Whenever I see a delta H, I like to say, okay, that's endothermic because it's positive. Right, and then they give us 1 mole is placed in a previously evacuated rigid 2-liter container. Calculate the pressure. So I'm immediately thinking, oh, Pivnert. It's not 100% of the time, but very frequently, very frequently, when it asks you to find pressure, it's Pivnert. It might be Dalton's law, but it's more frequently Pivnert. So pressure is what we're looking for. We have a 2-liter container. Make sure your volume's in liters. We have a 0.1 mole sample. The gas constant is 0.0821, and our temperature in Kelvin is 298. You just need to solve for P, which is 1.22 when you plug that in, ATM. Now we need to write the equilibrium constant for the decomposition of bromine. So you would do products over reactants. It doesn't specify whether it's KP or KC. So you could pick in this case. I'm going to use pressure because all of them are gases. But if it says KC, you have to use brackets. So pressure of BR2, pressure of Cl2 over the pressure of the BRCl squared. Coefficients become exponents. And then after the system has reached equilibrium, 42% of the original BRCl sample has decomposed. Determine the value of KEQ for the decomposition reaction. So I'm going to make an ice chart here. Squeeze it in, BRCl. Ice chart like this. Okay, so the BRCl, we started with that 1.22 ATM, and we didn't have any of the products to begin with. I know this is going to go down by 2x because of that coefficient of 2, and this will go up by x and up by x. Always use the coefficients. And then it says 42% of the original BRCl sample has decomposed. That means that I have, what, 58% left? I can subtract? Yeah, 58. So 58% of BRCl of the 1.22 is 0.71. That's remaining. Well, 0.72 if I'm 0.71. Anyway. So you can solve for x now. 1.22 minus 2x equals 0.71. And so we get that x is 0.26. So 0.26 and 0.26. Now that you have your equilibrium values, you can plug them back into your K expression. So the 0.26 squared, because they're the same on the top, over the 0.71 squared on the bottom, and you get 0.13 is your answer for E, or for D, F. I can't do my alphabet today. F. Okay, so they're just giving us this information again at the top. Calculate the bond energy of the BRCl bond using delta H for the reaction and the information in the following table. Anytime you see bond energy or bond enthalpy, it's the same thing. You always want to think it's broken minus formed. A lot of people try to do products minus reactants. That's not it. It's broken minus formed. And so the bonds between the BRCl have to be broken. So and then there's two of them, right? So 2 times our unknown X minus the bonds that are formed. And I'm going to add those together because both of those bonds are formed. And that's going to be equal to our overall in kilojoules per mole, so 1.6. So add, and then add that over to the 1.6 and divide by 2, and you'll find your value is 219 kilojoules per X there. Anytime you see bond energy or bond enthalpy, broken minus formed. Question 3 is the last of the long free response questions. Okay, so we have 50 milliliters of sodium carbonate of an unknown concentration. To determine the concentration, they mix it with excess calcium nitrate, causing a precipitate to form. That's great. Write a net ionic equation for the reaction that happens. So anything that's aqueous on both sides will be spectator ions. So our sodium is aqueous on both sides, and our nitrate is aqueous on both sides. So that leaves us with our carbonate ions and our calcium ions, forming our solid calcium carbonate. All right, so the diagram below is incomplete. Draw on the species needed to accurately represent the major ionic species remaining in the solution after the reaction has been completed. In the original instructions, they told us that we have some of this reacting with excess calcium nitrate. So because of that excess, not only are you going to have nitrate ions, you will also have calcium ions. And so you'll have, you want to make sure that you do it stoichiometrically. So 2 nitrate ions for every 1 calcium ion. So you would draw in a calcium and then another calcium. Nope, only 1, sorry. At least one of those needs to be used to make the solid calcium carbonate. So that's here. So I only want to use up some of that. Yeah, let me see what their points were. Yeah, it should just show 1 calcium ion because of the, if you're imagining that there were 2 to begin with that produced the 4 nitrates, one of those has to turn into the solid to react with the carbonate ion. Okay, so filter and dry the precipitate, record the data in the table, determine the moles of sodium carbonate in the original 50 milliliters of solution. This is going to take a couple steps now, right? We need to change this grams to moles using the molar mass, 0.93 grams, 100.1 grams per mole. So we have 0.0093 moles. And it was a 1-to-1 ratio between the calcium carbonate that was formed and the sodium carbonate to begin with. So we know that the moles are equal because it's a 1-to-1 ratio. From there, I can do just moles per liter to get the concentration. Nope, but that's it, right? I don't need to get the concentration. Sorry, I thought I was looking for molarity. So we just need to do the 0.0093 moles because it's the same. Now the student realizes the precipitate was not completely dried and claims that as a result the calculated molarity is too low. Do you agree and justify your answer? You should disagree with that. If there was extra water, that means this mass is too high. A higher mass leads to more moles and a higher molarity. So it is still an error for sure, but it would lead to your calculated molarity being too high. So make sure that you answer the question. Do you agree? No, because it would make the molarity too high. And then after the precipitate forms and it's filtered, the liquid that's passed through is tested to see if it can conduct electricity. What would be observed? You can even go back to your drawing from previously, and even if you didn't get the correct addition, they at least showed you the liquid that passed through the filter had those sodium ions and nitrate ions in it. As long as there's ions floating in the solution, it will conduct electricity. So it's because of those excess sodium and nitrate ions that are dissolved in the solution can conduct electricity. And some excess calcium ions. Okay, the student decides to determine the molarity using a different method. When it's dissolved in water, the carbonate ions hydrolyze to form HCO3 as shown in this equilibrium. And they give us the Kb expression and the Kb value. That's nice of them. So the student decides to determine the hydroxide ion concentration and use that result to calculate the initial concentration. Okay. Identify a laboratory method, not titration, that the student could use to collect data. This is so bizarre. This question threw so many people off because when you see acid-base reactions, you're going to think of titrations. So very few people wound up getting this, even though it's actually pretty straightforward. If you use something like a pH meter or an indicator to measure the pH, you can change pH to pOH, you can convert it, and then pOH to OH concentration. I don't think you'll see a question like that because this one caused a lot of controversy, but you can use the pH meter to measure hydrogen ion concentrations, hydroxide ion concentrations. You just have to do some calculations in between. So explain how the student could use the measured value to calculate the initial concentration of the CO3 negative. It says do not do numerical calculations. So you can, I would still say, hey, do an ice chart, because you don't have to calculate anything in your ice chart per se. You can just show it. If you know your hydroxide ion concentration, water doesn't matter because it's a liquid. We don't know the carbonate ion concentration, but we know that the carbonate is going to decrease by the same amount that the products are increasing. So if you do know the hydroxide ion concentration, we know that this is Y minus X. You can plug those values in to your Kb expression and solve for that unknown concentration Y at the beginning. So it winds up being 2.1 times 10 to the negative 4 is equal to whatever your concentration is over Y minus X. And if you solve for Y, you get it. I'm kind of curious how they explained it in the scoring guidelines, so let me look that up for you. They also did an ice chart, of course. Yes, so their written explanation is use a Kb expression and an ice table to determine the concentrations at equilibrium.
And the initial concentration is equal to the it's equal to the sum when you add the initial concentration. Yeah, it's just weird. I would do a nice chart. Definitely makes it easier. Okay, in the original Na2CO3 solution, is the concentration of the HCO3 greater than, less than, or equal to the concentration of CO3 to negative, and justify your answer. So let me rewrite the balanced equation for you guys because you need that. It is CO3, I'll write it down here, plus the water yields the HCO3 plus the hydroxide. And they give us the Kb value is 2.1 times 10 to the negative 4. So we know that it very much favors the reactants because this value is less than 1. So is in the original solution, we're comparing the HCO3 to the CO3 negative. The CO3 negative will be a larger concentration. So you'd say HCO3 is less than the CO3 negative because the value of Kb indicates that there's more reactants present. And then we need to make a buffer out of these things. Is this carbonate solution suitable for making a buffer with a pH of 6? And explain why or why not. So what you could do to figure this out is then find the pKb first. So you would take the negative log of the Kb, which is 3.68. And then you would subtract that from 14 to get the pKa. So 14 minus 3.68 is 10.32. So I would say that no, it's not particularly suitable for making a buffer with a pH of 6 because its pKa is so basic. It's so much higher than 7. It's very far away from that desired pH of 6. The best buffer solution with a pKa very close to the desired pH. Now we can transition to the short free response questions. There are 4 short free response and each one is worth 4 points. So now we're doing experiments with CO2. We have the sample of a gas in a rigid container. Student increases the temperature from 299 to 425. Describe the effect on the motion of the CO2 molecules. So they're going to move faster because they have a larger average kinetic energy. That's it. Higher temperature, higher average kinetic energy, greater speed. So then we need to calculate the pressure at 425. This is an application of the ideal gas law. So you could use Pivnert, but I think it's easier if you use P1 over T1 equals P2 over T2. It's not on the formula sheet, but you might want to remember it because it makes it a lot easier than trying to do the ideal gas law twice. This is the combined gas law, but we have a rigid container, so our volume is staying the same. So that's where I got the P1 over T1 equals P2 over T2. So now I can just plug in, originally it was at 0.7 at 299 Kelvin. What is the new pressure at 425? And it is 0.99 atm, which makes sense because you're increasing the temperature, you'll increase the pressure. So now we want to explain why the pressure changes as it's heated. Temperature affects pressure in 2 ways. At higher temperatures, they have more energy, so they're going to collide with a greater force. Also, because they're moving faster, they're going to collide with a greater frequency, so more often. So they were really looking for both of those things. They collide more frequently and with more force. Okay, so now the student measures the actual pressure and observes that it is less than the pressure predicted by the ideal gas law. Most of the time this pops up, your answer is going to be intermolecular forces. The CO2 molecules attract each other. That slows them down. So the two big deviations come from a non-negligible volume of the particles themselves, and then intermolecular forces of attraction showing up between the particles.
Question 5 is the next short free response.
So we have this complete photoelectron spectrum. Remember when you see these types of graphs, the one with the highest energy, highest binding energy, is always the 1s. And so, and S can hold 2 electrons. So that means this is 2, this is 4, this is 6. So those are the things that I always immediately will annotate on the graph. And so this is 1s, 2, and then the next one up is 2s, and then 2p6, and then 3s2, 3p6, 4s2. So, I mean, I annotated it on the graph, but it's the same thing here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And so our element, if I look at my periodic table, it's calcium, 20 electrons. So you could count the electrons or you could just look for the 4s2. Now for B, we want to calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell. Okay, so a couple of things here. You need to know the valence shell is this one. And then from there, I can use that energy to calculate the wavelength. But it takes 2 steps. So the equations, they are on your formula sheet. E equals HV. E is, they told us 0.98 times 10 to the negative 18. H is Planck's constant. Planck's constant is 6.63 times 10 to the negative 34th. Again, that's on your formula sheet. You don't have to remember it. So you just need to solve for the frequency. I'll divide that really quick. So 1.48 times 10 to the 15th. The unit for frequency is inverse seconds. Then you can do C equals lambda V. Lambda is wavelength. C is the speed of light on your formula sheet, 3 times 10 to the 8th. And we can plug in that frequency. And when we finally get the wavelength, which I'll write down here, we get 2.03 times 10 to the negative 7. And that was 2 points.
Question 6 is another short free response.
Okay, nitrogen dioxide. I'm sorry, this one's really small. Nitrogen dioxide is produced as a byproduct of the combustion of fossil fuels, and it decomposes according to that equation. The concentration is monitored as it decomposes and is recorded by the graph directly below. So this one, concentration over time graph. And then the 2 graphs that follow it are derived from the original data. Explain how the graphs indicate that the reaction is second order. So you're looking at the y-axis here, and you're looking for a straight line graph. This one is not a straight line. This one is not a straight line. This one is a straight line. So because it's 1 over the concentration versus time is the straight line graph, that's why it's a second order reaction. If the original one was a straight line, it'd be 0 order. If the natural log versus time is a straight line, then it'd be 1st order. But this one is 2nd. And then so we need to write the rate law for the decomposition. Well, you just told me it was 2nd order, so rate equals K. We start rate laws with rate equals K. And then our substance is NO2. And it's squared because it's 2nd order. So then consider 2 possible mechanisms for the decomposition reaction. Let me rewrite that rate law. Rate equals K NO2 squared because it's 2nd order. Okay. Is the rate law described by mechanism 1 shown below consistent with the rate law you wrote in part B? And justify your answer. So mechanism 1, first step is slow. So we only consider the first step. And we can ignore the fast step. And there are 2 molecules of NO2. So yes, that is consistent because there's 2 NO2s in the rate law. And you only look at reactants for rate laws. And that's it. So yes, it's consistent. There are 2 NO2 molecules in the slow step and nothing before the slow step. Same question. Is it consistent with the rate law that we wrote? And then, so this one, the slow step is the 2nd step, so I need to add these together. But when I add them, the N2O4 is an intermediate. And so you're left with, you still have 2 NO2s on the reactant side. Product sides doesn't matter for rate laws. So yes, it is consistent. It's also consistent because there's 2 NO2s when you add the slow plus anything before the slow.
And our last question of the whole exam is question 7. It's a short Fourier response as well.
So we have a 0.139 sample of oxalic acid. Then the student titrated it with KMNO4, which is a dark purple color. And the balanced chemical equation is shown above. Identify the species that was reduced and justify your answer in terms of oxidation numbers. Okay, so hydrogen in a compound is always +1. I'm going to write it below. Typically I'll write it above, but that's okay. So the Mn is the next one. Oxygen in a compound is always -2, unless it's a peroxide, but none of these are peroxides. So that means that this manganese must be +7 to cancel out the -8 from those 4 oxygens and still add up to -1 overall. You can ignore coefficients when you're doing oxidation numbers, but not the subscripts. And the manganese on this other side is +2 because it's the same as its charge when it's a monatomic ion. So already, without doing anything else, we know which one was reduced. The Mn that was in MnO4 was reduced because its oxidation number decreases from +7 to +2. So it was reduced, decreased. Okay, so there's our burette initial and final. I'm sorry, this one's also quite small on the screen. The student used a 50 milliliter burette until a faint lavender color was observed. An indication that the endpoint was reached. Write down the initial reading and the final reading and use them to determine the volume. So this is your sig figs question. Typically, there will be one question somewhere in the free response that has you measure something using the correct sig figs. You'd want to know all the ones that you know. So I know this is for the initial, I know it's 3 point something. I know it's 3.3 something because it's between the 3 and the 4 line. And then you estimate. It could be like 3.35. And if your last digit varies a little bit, that's okay. because that's your estimated digit. This one is 29.5 something. I'm going to say 5 as well. But you had to make sure that you're using 2 decimal places because of this device. And then when you subtract, let me see what their ranges were. Okay, so when you subtract to get your volume that was added, you would get a 26.2 milliliters. Volume down, we used 26.20 milliliters. And it says, given that the concentration was 0.0235, calculate the moles of the MnO4 ions that completely reacted. So you would change the milliliters to liters, 0.02620 liters, and multiply by the molarity. Liters times molarity gives you moles, which is for this one, it's real small, 0.000616 moles. You can use scientific notation if you want, but it's not required. Liters times molarity gives you moles. Very important to remember that one. Okay, a student proposes to perform another titration using a 0.139 gram sample of the oxalic acid, this time using a much smaller concentration in the burette. Would this titrant concentration be a reasonable choice to use if the student followed the same procedure and used the same equipment as before? Justify your choice. So a couple things you needed to notice from this one. It's the same mass of the original sample, so you have the same moles of the original sample. And that means you'll need the same moles of your titrant to get it to completely balance out. Well, if I have molarity is moles per liter, if I have 0.00143 molar titrant this time, and I have 0.00616 moles, I can solve for the liters there. And the liters that I get is 4.31 liters, or 4,310 milliliters. Given that it's a 50 milliliter burette, it is not a reasonable choice, because I would have to fill that burette up over and over and over and over and over again until I got to 4,000 milliliters. So no, it's not a good choice. A lot of people missed that point, but that was the last one on the test, so it might have been just like by the time you get to the end, you're kind of worn out, or they didn't really think about the practicality of it. So some of those questions will pop up.